Hello, welcome to my YouTube channel. In this video, we will build a top-down understanding of LLM policy optimization, why RLHF is needed, how it works, and how two important methods, PPO and GRPO, fit into the picture. My goal is to make the explanation as self-contained as possible. We'll start from the core intuition, connect it to the math, and then walk through one step of the training loop for each method. By the end of the video, you should have a clear mental model of how PPO and GRPO optimize LLM policies. Let's get started. Before we jump in, we first need to understand why supervised fine-tuning alone is not enough. In supervised fine-tuning, or SFT, we give the model a prompt together with a single reference answer, and train it to reproduce that answer token by token. The only signal is essentially copy this. This is useful, but notice what it leaves out. SFT only ever shows one good answer per prompt. It never shows a comparison. So it can teach the model to imitate a demonstration, but not to judge which answer is better. What we actually need is this. Given the same prompt and two candidate answers, A and B, the model should learn that humans prefer A over B. For large language models, this distinction is very important. To make a model more helpful, honest, and safe, we need preference feedback. This kind of preference feedback, learning from comparisons rather than demonstrations, is a core motivation for RLHF, or reinforcement learning from human feedback. This naturally brings us to another area of machine learning called reinforcement learning. The idea behind reinforcement learning is very similar to how humans learn. Since we were babies, we have learned by interacting with the world around us, trying things, observing the results, and gradually learn which actions lead to better outcomes. More formally, IL is a type of machine learning technique where an agent learns to make optimal decisions by interacting with an environment, receiving feedback via rewards or penalties. As shown in the diagram, starting from state S, the agent takes an action A. The environment then returns a reward R and transitions to a new state S'. From S', the agent takes the next action and the loop repeats. The goal of the agent is to learn a behavior that maximizes the total accumulated reward over time. Before we map reinforcement learning to language models, let's define a few key IL terms. First, the policy describes how the agent chooses actions. A trajectory is the sequence of states, actions, and rewards produced as the agent interacts with the environment. You will also often hear the word rollout. A rollout is basically a trajectory generated by running the current policy. So, trajectory describes the sequence itself, while rollout emphasizes the process of sampling it from the policy. The return is the total future reward from a given point onward. This is the quantity the agent ultimately wants to maximize. The value of a state is the expected future reward from that state. In other words, it tells us how good we expected things to be from here. Finally, the advantage tells us whether a particular action was better or worse than what we expected from that state. This will become very important when we discuss PPO later. Now let's map reinforcement learning to the case of large language models. In LLM reinforcement learning, the policy is the language model itself. Given the current context, the model defines a probability distribution over the next token. The state is the prompt together with the tokens generated so far. We can think of it as the current context seen by the model. The action is the next token sampled from the model. For example, suppose the prompt is "Where is Shanghai?" and the model has already generated "Shanghai is in." At this point, the state is the full context. Where is Shanghai? Shanghai is in. And the next action could be China. After the model chooses that action, the state changes. Now the generated prefix includes China, and the model uses this new context to choose the next token. One clarification before we continue. In this slide and in the examples later, I will often write tokens as if each word is one token. This is only for simplicity. In real language models, tokenization is more complicated. A token can be a full word, part of word, punctuation, or even include white space. But conceptually, the IL formulation is the same. So, LLM generation can be viewed as a sequence of decisions. At each step, the model observes the current context, chooses the next token, and then moves to a new state. In RLHF, we optimize this policy so that the generated answers receive higher rewards according to human preferences. So, how do we usually apply reinforcement learning to language models? A classical example is InstructGPT from OpenAI, which introduced the RLHF pipeline for aligning language models with human preferences. RLHF usually contains three main stages. The first stage is supervised fine-tuning, or SFT. Here, we collect demonstration data and train a supervised policy. The second stage is reward modeling. In this stage, we collect comparison data where humans compare different answers to the same prompt, and then we train a reward model to predict which answer is preferred. The third stage is reinforcement learning. Here, we optimize the policy model against the reward model, so that the model learns to generate answers that receive higher preference scores. So in summary, the RLHF pipeline is supervised fine-tuning, reward modeling, and reinforcement learning. Let's go through these steps one by one. Most of us are already familiar with the pre-training and supervised fine-tuning stage of language models. During pre-training, we train the model on a very large collection of text data, such as web pages, books, code, articles, and many other sources. The objective is simple. Given the previous tokens, predict the next token. Supervised fine-tuning, or SFT, is teacher first, next token prediction on a reference answer. Same objective as pre-training, but the data is prompt and answer pairs instead of arbitrary text. The goal is to make the model more useful as an assistant by teaching it how to answer questions or following instructions. Suppose Q is the prompt and O is the target answer. We concatenate the tokens from Q and O and feed the full sequence into the language model. At each position, the model predicts the next token. So the target sequence is basically the input sequence shifted by one token. This shifted setup is exactly what teacher first means. At every position, the model is showing the true previous token from the reference answer as input, rather than its own previous predictions. So even if the model would have generated a different token, training continues along the reference sequence. More specifically, the training objective is the standard cross-entropy loss, or equivalently, the negative log likelihood of the target tokens. For each position, the model predicts a probability distribution over the vocabulary, and we want it to assign high probability to the correct next token. The important difference from pre-training is that in supervised fine-tuning, we usually compute this loss only on the answer tokens. The prompt tokens are used as context, but they are masked out from the loss. So the SFT loss encourages the model to generate the target answer conditioned on the prompt. For reward modeling, the first thing we need to do is to collect comparison data. The idea is simple. For the same prompt, we generate multiple candidate answers. We can do this by sampling from the same model several times with a non-zero temperature, or by collecting answers from different models. Then we ask a human labeler to compare these answers and rank them from best to worst. For example, suppose the prompt is "Explain the moon landing to a 6-year-old." We generate 4 different answers, A, B, C, and D. Here, 4 answers is just an example. In practice, it is usually a small number, often somewhere between 4 and 9. After reading them, the human labeler ranks them from best to worst as C, then A, then D, and finally B. From this ranking, we can construct pairwise preference examples. Since there are 4 answers, we get 6 pairs. C is preferred over A, C is preferred over D, C is preferred over B, A is preferred over D, A is preferred over B, and D is preferred over B. These pairwise comparisons are the training data we will use to train the reward model. Now let's see how we train the reward model using the preference data we collected. The reward model takes a prompt Q and an answer O and outputs a single scalar reward score. Intuitively, a better answer should receive a higher reward score. In practice, the reward model is usually initialized from the SFT model. We reuse the language model backbone, remove the original language model head that predicts the next token, and add a reward model head instead. This head converts the hidden state of the final token into one scalar reward score for the whole answer. For each preference pair, we have 2 answers: the chosen answer, which humans prefer, and the rejected answer, which humans prefer less. The reward model gives us 2 scores, 1 score for the chosen answer and 1 score for the rejected answer. We want the chosen answer to get a higher score than the rejected answer. To train this, we use the Bradley-Terry model. The Bradley-Terry model is a probabilistic model for pairwise comparison. It says that if 2 candidates have scalar scores, then The probability that one candidate is preferred over the other depends on the difference between their scores. In our case, the probability that the chosen answer is preferred over the rejected answer is computed as the sigmoid of the reward difference, the reward of the chosen answer minus the reward of the rejected answer. If the chosen answer is much larger than the rejected answer, the difference is very positive, the sigmoid is close to 1, and the loss is close to 0. This means the reward model is already assigning the correct preference. If the chosen answer is smaller than the rejected answer, the difference is negative. The sigmoid is close to 0, and the negative log loss becomes very large. So the model is strongly penalized. So the reward model loss is the negative log probability of the human preference pairs under the Bradley-Terry model. In practice, we compute this loss for each chosen rejected pair and average it over the batch. One practical detail is that different prompts in the training dataset may produce different numbers of preference pairs. To handle this, we may first average the loss over the pairs from the same prompt and then average across prompts. This prevents prompts with more candidate answers for dominating the batch. Now that we know how to train a reward model, we can move to the final stage of RLHF, reinforcement learning. In this stage, we use the reward model as a training signal to optimize the language model policy. The goal is to make the model generate answers that receive higher reward scores. In the rest of this video, I will introduce two reinforcement learning methods commonly used for LLM policy optimization. The first one is PPO, which stands for Proximal Policy Optimization. PPO is the more classical and widely used RLHF algorithm. The second one is GRPO, which stands for Group Relative Policy Optimization. GRPO is simpler in some ways because it removes the value model and uses group relative rewards instead. Let's start with PPO. There are 4 models involved in PPO. The first one is the policy model. This is the language model we want to optimize. For an LLM, the policy gives us the probability of the next token, condition on the prompt, and the tokens generated so far. The second one is the reference model. This is usually a frozen copy of the model before IL training. It anchors the policy to what it learned during SFT, preventing it from drifting too far and losing its general capabilities. The third one is the reward model. This is the model we trained in the previous step. It gives a reward score for the 4 answers generated by the policy model. The first one is the value model. The value model predicts the expected future reward from the current state, and it is used to compute the advantage. At a high level, PPO works like this. First, the policy model generates an answer O from a prompt Q. Next, we compute a KL penalty by comparing the current policy to the reference model. We also score the answer using the reward model. The KL penalty and the reward score are then combined into the final reward signal R. Separately, the value model produces value estimates V. The reward signal R and the value estimates V are then used to compute the advantage A with a method called GAE. Finally, this advantage signal tells us how to update the policy model. As we mentioned earlier, in PPO, the reward signal usually combines two parts: the final reward model score I-Phi of Q and O and a per token KL penalty. The reward model gives one score for the whole generated answer, but in LLM PPO, each generated token is treated as an action. So we need token-level quantities such as log probabilities, KL penalties, and advantages. Since the reward model score is only available for the complete answer, we add it at the final token. For all tokens before the last token, the step reward is just a minus beta times the per token KL estimate. For the final token, the reward is the reward model score for the full answer minus beta times the per token KL estimate on the last token. That per token KL estimate is computed with the K1 estimator. For each generated token, we compare its probability under the current policy pi theta with its probability under the reference model pi ref, giving the same context. Here, beta controls the strength of the KL penalty. A larger beta keeps the policy closer to the reference model, while a smaller beta allows the policy to move more aggressively toward answers with a higher reward. So, the KL penalty acts as an anchor to the reference policy. It prevents the current policy from drifting too far during reinforcement learning optimization. Now let's look at the value model in more detail. The value model estimates the expected future return from the current state ST before taking action AT. In the LLM setting, the state ST is the prompt together with the generated tokens so far. The action AT is the next token. Architecturally, we can think of the value model as an LLM backbone with a value head on top. This value head predicts a scalar value for each generated token position. In practice, this does not always mean we train a completely separate model just for value prediction. Very often, the policy model and the value model share the same transformer backbone. The policy head predicts the next token distribution, while the value head predicts the scalar value. So, conceptually, we talk about a policy model and a value model, but implementation-wise, they may share most of their parameters. The return from step T, written as JT, is defined recursively as the current reward RT plus gamma times the future return GT plus 1. Equivalently, it is the discounted sum of future rewards from this step onward. Here, gamma is the discount factor. Intuitively, this is like preferring to receive money sooner rather than much later. Future rewards are still valuable, but they may be discounted. In standard reinforcement learning, gamma is usually between 0 and 1. A smaller gamma discounts future rewards more strongly, while a gamma close to 1 preserves more of the future reward. In many LLM RLHF settings, gamma is often set close to 1, or even exactly 1. The reason is that the main reward often comes from the final complete answer. But earlier tokens are also important because they determine the structure, direction, and the reasoning path of the answer. So we usually do not want to discount the final reward too much when assigning credit to earlier tokens. Also, unlike some traditional IL problems, the generated answer has a finite length. So, using gamma close to 1 is usually reasonable. So, Vt, the value model V psi applied to state St, is the expected return Jt from that state. Intuitively, this means, given the partial answer so far, how good do we expect the final outcome to be? To train the value model, we feed these predictions to the returns. The value model loss is the mean squared error between the predicted value V psi of St and the target return Jt, averaged over the generated tokens. The value estimate will later help us compute the advantage, which tells us whether the sampled token was better or worse than expected. Let's look at a simple example to better understand the value model. Suppose the prompt Q is explain gravity simply, and suppose the generated answer O is gravity pulls objects together. Here, we continue using the simplification that each word is 1 token. So this answer has 4 tokens. Now, suppose the reward model score for this prompt answer pair I phi of Q and O is 2. We also have a per token sampled KL estimate 0.03, 0.02, 0.04, and 0.01. If we set beta equals 1, then the step reward are calculated like this. For the first 3 tokens, the reward is only the negative KL penalty. So we get R1 equals minus 0.03, I2 equals minus 0.02, and I3 equals minus 0.04. For the final token, we add the reward model score for the complete answer. So R4 equals 2 minus 0.01 equals 1.99. Next, suppose the discount factor gamma equals 1. This means we do not discount the future rewards. We can compute the returns backwards from the final token. First, J4 equals R4 equals 1.99. Then J3 equals R3 plus J4 equals minus 0.04 plus 1.99, which equals 1.95. J2 equals R2 plus J3 equals minus 0.02 plus 1.95 equals 1.93. And finally, J1 equals R1 plus J2 equals minus 0.03 plus 1.93, which equals 1.90. These returns become the training target for the value model. At each position, the value head predicts a scalar value, and we want that prediction to match the corresponding return Jt. Plugging this in, the value model loss is the mean squared error between each predicted value, V psi of St, and its target return Jt. Here, average over the 4 tokens of this answer. Now let's introduce GAE, which stands for Generalized Advantage Estimation. Before we define GAE directly, let's first set up the reinforcement learning objective. Suppose tau is a trajectory. It contains a sequence of states and actions S0, A0, S1, A1, and so on. This trajectory is generated by following the policy πθ. At each time step t, the action AT is sampled from the policy conditioned on the current state ST. After the agent takes action AT, the environment transitions to the next state ST plus 1, according to the environment transition probability P. At each step, the agent also receives a reward RT, which depends on the current state, the action, and the next state. The goal of the reinforcement learning is to maximize the expected return. We write this objective as G theta. It is the expected accumulated reward over trajectories sampled from the current policy πθ. In other words, we want to adjust the policy parameters theta so that on average, the trajectories generated by the policy receives higher total reward. Now let's compute the gradient of this objective. Our objective G theta is the expected return over trajectories sampled from the policy. By the definition of expectation, we can write this as integrate over all possible trajectories, the probability of the trajectory πθ of tau multiplied by the return of that trajectory J of tau. Now we want to take the gradient with respect to theta. To do this, we apply the chain rule to the log probability. The gradient of a probability equals the probability itself multiplied by the gradient of the log probability. So the gradient of pθ of tau becomes pθ of tau times the gradient of log pθ of tau. After applying the chain rule, the gradient becomes integrate over all possible trajectories, the probability of the trajectory πθ of tau multiplied by the gradient of the log probability of the trajectory multiplied by the return J of tau. Now we expand the probability of a trajectory. A trajectory starts from an initial state, then at each step, the policy chooses an action and the environment moves to the next state. So the probability of the trajectory is the probability of the initial state P of S0 multiplied by all the policy probabilities πθ of AT given ST multiplied by all the environment transition probabilities P of ST plus 1 given ST and AT. If we take the log of this trajectory probability, the products become sums. So we get three parts: the log probability of the initial state plus the sum of the log policy probabilities plus the sum of the log environment transition probabilities. But only the policy depends on the theta. The initial state distribution and the environment transition probability do not depend on theta. Therefore, when we take the gradient with respect to theta, those two parts disappear, leaving the gradient of the sum of log πθ of AT given ST. Since the gradient distributes over the sum, this becomes the sum over time of the gradient of log πθ of AT given ST. Putting this back into the objective, we get the policy gradient. It is the integral over all possible trajectories of three terms multiplied together. the probability of the trajectory pi theta of tau, the sum of the gradient of the log action probabilities, and the return g of tau. This equals to the expectation of g tau multiplied by the sum of the gradients of the log action probabilities. We can tighten this and more generally weight each term by replacing the full trajectory return g tau with a per step signal psi t. The policy gradient then becomes the expectation of a sum over time, where each gradient of the log action probability is weighted by its own psi t. So the key question becomes, what should this weighting signal be? Now let's connect this to advantage estimation. Policy gradient methods estimate the gradient of the expected return by weighting each action's gradient with a per step signal psi t. A good choice of this weighting signal is the advantage A pi theta of STAT. It is defined as Q pi theta of STAT minus V pi theta of ST. This choice reduces variance by subtracting a baseline. Here, Q pi theta of STAT is the expected return if we take action AT at state ST and then continue following policy pi theta. V pi theta of ST is the expected return from state ST, averaging over actions sampled from policy pi theta. So the value function acts as a baseline. Therefore, the advantage tells us how much better than average is action AT in state ST according to the current policy. This baseline is important because it reduces variance. For example, imagine two prompts. Prompt A is easy, so most completions get high scores. Prompt B is hard. Even the best completions may get relatively low scores. If we only look at raw reward, the easy prompt may always look good and the hard prompt may always look bad. But what we really want to know is whether a completion is better or worse than expected for that specific prompt. By subtracting a baseline, the advantage signal reflects better than expected quality, not just prompt difficulty. In practice, however, the true advantage function is unknown, so we need to estimate it. This is where GAE comes in. Now let's see how we estimate the advantage with GAE. First, we define the temporal difference residual, or TD residual for short. The TD residual is a one-step estimate of the advantage. It is written as delta t, and it compares two quantities. What the value model predicted before, and what we observe after taking one step. More specifically, delta t equals the reward at step t plus gamma times the value of the next state minus the value of the current state. Intuitively, this tells us whether the outcome was better or worse than what the value model expected. If delta t is positive, the result was better than expected. If it is negative, the result was worse than expected. GAE combines these TD residuals across multiple future steps. It takes an exponentially weighted sum of future TD residuals. The recursive form is the one we usually implement. The advantage at step t equals delta t plus gamma times lambda times the advantage at the next step. Here, lambda controls the bias-variance trade-off. When lambda equals 0, GAE becomes pure one-step TD estimation. This has lower variance but higher bias because it only looks one step ahead. When lambda equals 1, GAE becomes closer to Monte Carlo estimation. This has lower bias because it uses the full rollout, but higher variance because the estimate depends on many sampled future rewards. In practice, lambda is often set to a value like 0.95, which gives a balance between bias and variance. Finally, we now have all the building blocks needed to apply PPO to a language model. The PPO objective is something we want to maximize. At a high level, we want to increase the probability of tokens with positive advantage and decrease the probability of tokens with negative advantage. The formula may look complicated at first, but the idea is simple. We want to update the current policy using rollouts generated by the old policy, while making sure the update is not too large. But why do we use rollouts from the old policy instead of the current policy? We will explain that next when we discuss the importance ratio. In this objective, we sample a prompt Q from the prompt dataset, and then sample an answer O from the old policy, pass theta old. For each generated token, we compute two surrogates, an unclipped one and a clipped one. The unclipped surrogate is the importance ratio IT theta multiplied by the advantage AT. Here, RT theta is the probability of the current action under the current policy divided by the probability of the same action under the old policy. Pass theta of AT given ST over pass theta old of AT given ST. In the LLM setting, this becomes pass theta of OT given Q and O less than T over pass theta old of OT given Q and O less than T. The clipped surrogate is similar, but we clip the importance ratio so that it cannot go below 1 minus epsilon and cannot go above 1 plus epsilon. PPO takes the minimum of the two surrogates. This clipping is the key idea of PPO. It prevents the new policy from moving too far away from the old policy in one update. Finally, the 1 over size O factor averages this objective over the tokens of the answer, and the outer expectation averages over the batch of prompts. Here, AT is the advantage term we introduced earlier in the GAE section. It tells us whether this sampled token was better or worse than expected. If this formula still feels abstract, don't worry. In the next few slides, we will break down the three important parts: the importance ratio, clipping, and how the advantage AT is computed in practice. So, why do we generate the rollout using the old policy instead of the current policy? Well, the reason is efficiency. In pure on-policy training, every time the policy changes, we will need to generate fresh rollouts from the new policy. But for large language model, rollout generation is expensive, especially for long answers or long horizon tasks. So, in PPO, we first make a frozen copy of the current policy and call it the old policy, denoted as pass theta old. Then, we use this old policy to generate a batch of rollouts. After the rollouts are generated, we optimize the current policy pass theta using this fixed batch of data. This means we allow a small, controlled, off-policy mismatch. So, here is the problem. The rollouts came from the old policy pass theta old, but the model we are updating is the current policy pet theta. To correct this mismatch, we multiply the advantage AT by the importance ratio RT theta. This ratio compares how likely the sample token is under the current policy versus under the old policy. Multiplying by this ratio corrects the mismatch between the policy that generated the rollouts and the policy being updated. But we don't want this ratio to become too large or too small. That is why PPO introduces clipping. Now let's take a closer look at what PPO clipping is doing. This plot shows the objective for a single time step t. The horizontal axis is the importance ratio R, which compares the probability of the token under the current policy with the probability under the old policy. The red dot indicates where the PPO update starts on this curve. At this initial point, the ratio R equals 1, because before the update, the current policy is the same as the old policy. Now consider the cases when the advantage is positive. A positive advantage means this token was better than expected, so we want to encourage the model to produce it more often. To maximize this objective, PPO want to increase this importance ratio, meaning the current policy should assign a higher probability to this token than the old policy. But PPO does not want this increase to go too far. Once R is larger than 1 plus epsilon, the objective becomes clipped. So, increasing the probability even more gives no additional gradient signal. On the other hand, if R is much smaller than 1 minus epsilon, it means the probability of a gold token has dropped too much. In that region, we keep the unclipped objective active, so the gradient can push the ratio back up. Now consider the case when the advantage is negative. A negative advantage means this token was worse than expected, so we want to discourage the model from producing it. Since AT is negative, the surrogate R times AT becomes less negative when R decreases. So, to maximize the objective, PPO wants to decrease the importance ratio, meaning the current policy should assign a lower probability to this token than the old policy. But again, PPO does not want the update to go too far. Once R is smaller than 1 minus epsilon, the objective becomes clipped. So, reducing the probability even more gives no additional benefit. And if R is larger than 1 plus epsilon, it means the probability of a bad token is still too high. In that region, the unclipped objective remains active, so the gradient can push the ratio back down. So the key idea is, PPO clipping allows useful updates, but it prevents the policy from changing too aggressively in one optimized step. Now let's briefly recap how the advantage AT is computed. AT comes from applying GAE, generalized advantage estimation, to two inputs: the per token rewards from the current step onward and the learned value function Vci. The first input is the per token reward RT in PPO for RLHF. This reward combines the per token KL estimate KLT and the final token, the reward model score I5 of Q and O. Here, KLT measures how much the policy deviates from the reference model at token T, and beta times KLT is the penalty term we subtract from the reward. The second input is the value model. For each state, the value model predicts a scalar value Vt, With these two inputs in hand, GAE produces the advantage in two steps. First, we compute the TD error delta t, the reward at step t plus gamma times the value of next state minus the value of the current state. Then we compute the advantage backward. AT equals delta t plus gamma times lambda times AT plus 1. Finally, to conclude the PPO section, let's walk through one step of the PPO training loop. First, we copy the current policy pet theta and freeze it as the old policy, pet theta old. Then, for each prompt Q, we sample an answer O from the old policy. This answer is a sequence of generated tokens, O1, O2, and so on up to OT. Next, we compute the reward model score for the complete answer, I of Q and O. This gives us one scalar reward score for the full response. Then, for all response tokens, we compute several token-level quantities in parallel. First, the value model predicts a value Vt, where the state St is the prompt plus the generated tokens before position t. Second, we compute the per token KL estimate, KLT. Conceptually, this compares pet theta with the reference policy. We use log pet theta old here because at rollout time, the old policy is a frozen copy of pet theta, and we already have its log probabilities from generation. Using the reward model score and the KL estimate, we form the step reward RT. For tokens before the final token, the reward is just the negative KL penalty. For the final token, we add the reward model score for the complete answer. Once we have the step reward RT and the value predictions, we compute the TD error. Delta t equals RT plus gamma times the next value Vt plus 1 minus the current value Vt. At the final token, the next value Vt plus 1 is 0 because the answer ends here. Because the answer ends there and there is. Because the answer ends there and there is no next state. Next, we compute the advantage and use it to update the model. Starting from the final token and move backward, we compute the advantage AT using the recursive GAE formula. The advantage at step t equals the TD error delta t plus gamma times lambda times the next advantage AT plus 1. We initialize the recursion with A capital T plus 1 equals 0. We also compute the return target JT, which is used to train the value model. Remember, advantage is defined as return minus value. So, after we estimate the advantage, we can add the value baseline back. JT equals AT plus VT. With JAE, this is an estimated return target that reuses the value baseline. During PPO optimization, we then recompute the current policy log probability on the same rollout. In other words, for each generated token OT, we compute its log probability under the current policy pet theta, giving the prompt Q and the previous generated tokens. Then, we compute the importance ratio RT theta. This is the exponential of the current policy log probability minus the old policy log probability for the same token and the same context. Finally, we calculate the training loss. Since GPPO is an objective we want to maximize, in implementation, we minimize the negative PPO objective. We also add the value model loss weighted by a coefficient CT. As we mentioned before, the policy model and the value model often share the same transformer backbone, with one head for next token prediction and another head for value prediction. During PPO training, we usually update the shared backbone and both heads together. The reward model I-Phi and the reference model pi theta stays frozen. Now let's move from PPO to GRPO, which stands for Group Relative Policy Optimization. Compared with PPO, GRPO uses a simpler setup. Recall that PPO involved 4 models: the policy model, the reference model, the reward model, and the value model. GRPO keeps only 3 of them. The value model is dropped. The first is the policy model pi theta. This is the language model we want to optimize. For an LLM, the policy gives us the probability of the next token conditioned on the prompt and the previous generated tokens. Because GRPO samples a group of answers per prompt, we index by both the answer I and the token position T. The second is the reference model pi-ref, a frozen copy of the model before IL training, used to anchor the KL penalty. The third is the reward model I-Phi, the model we trained earlier, which scores complete answers. The value model V-Psi, GRPO removes it entirely. And because there is no value model, we also do not need GAE to estimate the advantage. Instead, GRPO computes the advantage from a group of sampled answers. We will see how on the next slide. Now, let's see how GRPO computes the advantage. For each question queue, we sample a group of answers from the old policy pi theta old. We denote them as O1, O2, and so on up to OG. Then, the reward model scores each answer, give us G reward scores, R1, R2, and so on up to RG. Instead of using a value model as the baseline, GRPO uses the rewards within the same group. For each answer I, we compute its normalized reward by subtracting the mean reward of the group and divide by the standard deviation of the group rewards. This normalized reward becomes the advantage for that answer. Then, we assign the same advantage to every token in that answer. So, if an answer gets a higher reward than the group average, it has a positive advantage, and the GRPO will encourage the model to generate answers like this. If an answer gets a lower reward than the group average, it has a negative advantage, and GRPO will discourage it. This is what group as baseline means. The reward is judged relative to a group of answers for the same prompt instead of relative to a learned value model. The GRPO objective is very similar to the PPO objective, but adapted to the group setting. Instead of sampling one answer from each prompt, we sample a group of G answers from the old policy pi theta old. And then, for each answer in the group and for each token in that answer, we compute the importance ratio RIT theta. This ratio compares the probability of token OIT under the current policy pi theta with its probability under the old policy pi theta old, giving the same prompt and the previous tokens. The advantage AIT is computed using the group relative reward we introduced in the previous slide. The clipping part is the same as PPO. It prevents the current policy from moving too far away from the old policy during one update. One difference from the PPO version we discussed earlier is how the KL term is used. In PPO, we included the KL penalty inside the reward signal. In GRPO, the KL penalty is subtracted directly in the objective as a separate regularization term, and we use the K3 estimator for the KL term. Specifically, K3 approximates the KL as rho minus log of rho minus 1. Here, rho is the ratio of reference to current probability for the token, pi ref of OIT divided by pi theta of OIT. Compared with the K1 estimate we used in PPO, the K3 estimator is always non-negative and usually has lower variance. So, in short, GRPO keeps PPO-style clip objective, removes the value model, replaces the value baseline with a group relative baseline, and adds the KL penalty directly in the objective. Let's walk through one step of GRPO training loop similar to what we did for PPO. First, we copy the current policy pi theta and freeze it as the old policy pi theta old. Then, for each prompt Q, we sample a group of answers from the old policy, O1, O2, etc., and OG. Next, we use a reward model or more generally a reward function to score each answer. This gives us a group of reward scores R1, R2, etc., and RG, where Ri is the reward score for prompt Q and answer OI. Then, for each answer in the group and for each token in that answer, we compute several quantities in parallel. First, we compute the importance ratio RIT theta, which compares the probability of the token under the current policy and the old policy. Second, we compute the advantage AIT. This comes from the group relative reward. We normalize each answer's reward by subtracting the group mean and divide by the group standard deviation, and then assign that advantage to every token in the same answer. Third, we compute the per token KL term between the current policy and the reference model. This KL term is multiplied by beta and subtracted from the GRPO objective as a regularization term. Finally, we calculate the training loss. Since GRPO is an objective we want to maximize, in implementation, we minimize the negative GRPO objective. During GRPO training, we update the policy model pi theta. The reference model pi ref stays frozen, and the reward source, either a reward model or a reward function, is not updated by GRPO. At a high level, what is the difference between PPO and GRPO? The biggest difference is the choice of baseline. PPO uses a learned value model, or CRIDIC, as baseline. GRPO uses the group of sampled answers as the baseline. This leads to different characteristics for the two methods. PPO learns a value model and estimates the advantage at the token level. It is more general, but it also has a heavier training pipeline because we need to train and update both the policy model and the value model. GRPO, in contrast, does not need a value model. Instead, it samples multiple completions for the same prompt, scores them, and normalizes the reward within the group. Because of this, GRPO is usually simpler and cheaper to train. So intuitively, PPO asks, was this token better than my value estimate? GRPO asks, was this answer better than the other answers from the same prompt? So when should we choose PPO? PPO is a good choice when token level credit assignment matters. Specifically, the reward model usually gives one score for the whole answer, not one reward per token. PPO uses the value model and GAE to propagate that sequence level reward backward and estimate token level advantages. This is especially useful for long outputs, or cases where different parts of the answer may contribute differently to the final quality. PPO is also useful when the reward variance within a group of sampled answers is low. In that case, group normalization may not give a strong baseline, and a learned value model can be more robust. Another reason to choose PPO is stability. PPO is a more mature and widely tested recipe for general RLHF training. So, the typical use case is general RLHF for assistant alignment, making the model more helpful, honest, and harmless. Then, when should we choose GRPO? GRPO is a good choice when outcome-level supervision is enough. In other words, we only need to know whether the final answer is good or bad, instead of estimating detailed token-level advantage with a value model. GRPO also works well when rewards within the sampled group spread out naturally. For example, in math or code task, some completions may pass the verifier or unit test, while others fail. This gives a clear relative signal within the group. Another advantage is simplicity. GRPO does not need a value model, and it does not need GAE, so the training pipeline is simpler and cheaper. This makes GRPO especially suitable for math, code, and other verifiable tasks. That pretty much covers everything I want to share in this video. We started from the motivation for RLHF, then went through supervised fine-tuning, reward modeling, PPO, and finally GRPO. Of course, this video only gives a high-level walkthrough, so I strongly recommend reading the original papers if you want to understand the design choices and the details more deeply. If you have any questions, please leave a comment. If you find this video useful, please like it and share it with others. Thanks for watching, and I'll see you next time. Bye!